Welcome to The Explainer. Today, we're tracking a colossal, escalating threat to our atmosphere, and we're evaluating humanity's ultimate proposed secret weapon to fight it. If you're prepping for your A-level geography exams, this is absolutely the exact synthesis of physical systems and human mitigation strategies that you need to master. Let's get into it.
Here's our roadmap for today. We'll start with the carbon combustion problem, then track CO2 using the famous Keeling Curve, look at carbon capture and storage, or CCS, debate its overall effectiveness, and finally, deliver our verdict on CCS.
Section 1. The carbon combustion problem.
All right, let's dive right into our main antagonist here, the process of fossil fuel combustion. Now, to really understand the global carbon cycle, we have to start at the chemical level. Combustion is a high-temperature exothermic reaction. Simply put, that means it generates heat. When carbon-rich fossil fuels like coal, oil, or natural gas react with oxygen, they release that trapped energy as heat and light. But crucially, they also generate a byproduct. It's a mixture called smoke, and that contains water vapor and our major greenhouse gas, carbon dioxide.
You've probably seen the classic fire triangle before. It brilliantly illustrates exactly what's needed for this reaction to happen: fuel, oxygen, and heat. The problem is, when we trigger this on a massive industrial scale across the globe, it causes this rapid, overwhelming transfer of carbon. For thousands of years, the Earth's carbon cycle just existed in this beautiful state of dynamic equilibrium. But industrial combustion? Well, it's a violent human intervention that completely disrupts that balance.
Take a look at this detailed global carbon cycle system. It shows how human activity literally rips ancient carbon right out of geological sedimentary rock stores, places where it's been safely locked away as fossil fuels for up to 300 million years, and fires it straight up into the atmosphere. Notice that specific red flow line labeled human activity. We are currently injecting an estimated 9 gigatons of carbon into the atmosphere every single year. That is a massive unidirectional flow that nature just cannot buffer fast enough.
Section 2. Tracking CO2 with the Keeling Curve. Now, to defeat any threat, you first have to track its power level, right? Which brings us to Charles Keeling and his monumental geographical discovery. Back in 1958, Keeling set up his base of operations at the Mauna Observatory in Hawaii. You might be wondering why Hawaii? Well, notice its location on the map. It's incredibly remote, thousands of miles from major industrial centers in places like California or Japan. Plus, the observatory itself sits at a staggering elevation of 3,400 meters above sea level. This high altitude provides perfectly mixed, super clean air that's completely isolated from local pollution sources. Basically, it is the absolute ideal location to capture a true, unbiased average of our global atmospheric composition.
And thanks to Keeling's daily measurements, we have this pristine record of exactly what combustion is doing to our air. Before the Industrial Revolution, ice core records tell us that atmospheric CO2 rested in equilibrium at around 280 parts per million. But, thanks to relentless global combustion, our threat level breached the devastating 400 parts per million threshold back in 2014. To put that into perspective, the last time the Earth saw CO2 concentrations above 400 ppm was during the Pliocene period. That's long before the Quaternary ice ages. We're talking millions of years ago.
So here it is, the Keeling Curve. It's arguably one of the most famous graphs in all of science, and it reveals two really distinct patterns. First, there's that terrifying, relentless long-term upward trend, proving beyond a shadow of a doubt that fossil fuel use is fundamentally changing our atmosphere. But look closer at the line itself. Notice how it's not smooth? It has these distinct, jagged seasonal oscillations.
Those jagged teeth in the curve actually represent the Earth literally breathing. Because most of the planet's landmass, and therefore most of its vegetation, is located in the northern hemisphere, the global carbon cycle has a seasonal rhythm. In the northern spring and summer, explosive plant growth absorbs massive amounts of CO2 from the atmosphere via photosynthesis, which causes a temporary dip in the graph. But then, in the autumn and winter, as leaves fall and biomass decays, all that CO2 is released back into the air, causing the spike. It's an incredible natural cycle, but it is currently being completely overwhelmed by that baseline upward trend of human emissions.
Section 3. Carbon Capture and Storage, or CCS.
With this threat level constantly escalating year after year, engineers and geographers are working on a high-tech secret weapon, carbon capture and storage. CCS is a seriously ambitious mitigation strategy. The fundamental idea is this: what if humanity could just keep benefiting from the cheap, abundant energy of burning fossil fuels, but magically intercept the smoke?
CCS is designed to forcefully capture that CO2 right at the source and sequester it, which just means lock it away permanently back into geological stores, like depleted oil and gas reservoirs, instead of letting it escape into the sky.
This technology builds into a critical three-step mechanism that you absolutely need to nail for your exams. Step 1 is capture. This means separating the CO2 from the rest of the power station's emissions right at the smokestack. Step 2 is transport. The captured gas is heavily compressed into a liquid-like state and moved via specialized pipelines. And finally, step 3 is geosequestration. That compressed carbon is forcefully injected deep underground or even below the ocean floor into porous rocks for permanent, secure storage.
Section 4. Debating CCS effectiveness.
Now, on paper, this sounds like the ultimate solution, right? But is this secret weapon actually viable out there on the real-world battlefield, or is it just an incredibly expensive pipe dream? It is time for a high-stakes evaluation. For your essays, you can't just describe what CCS is. You have to critically judge it. You need to pit its massive theoretical potential against its severe structural flaws. So let's lay out the debate.
Let's break down the arguments. On the pro side, the mitigation potential is pretty staggering. A fully functional CCS system could wipe out up to 90% of a coal power station's carbon emissions. And the IPCC estimates that CCS could provide up to 55% of the world's total carbon mitigation effort by the year 2100. It fundamentally reverses our disruption of the carbon cycle by putting the carbon right back where we found it. However, on the con side, the technology is incredibly complex and still largely unproven at a true global scale. Plus, for the whole system to work, that carbon has to stay trapped underground literally forever. If a seismic event or some structural failure causes a massive volume of that highly compressed CO2 to leak back to the surface, it poses a severe, immediate, and potentially catastrophic risk to local ecosystems and the atmosphere.
And honestly, the structural limitations go even deeper than that. Cost is a huge barrier. The UK government actually had to cancel major pilot projects that were intended to store carbon in the North Sea, simply because the costs soared to over $1 billion US. Moreover, there's a massive flaw on the scale of application here. CCS targets power stations, but power stations only account for about 25% of global greenhouse gases. That leaves massive sectors like transport, manufacturing, and agriculture, which make up 60% of emissions, completely untouched by CCS. Because of all this, critics strongly argue that rather than spending trillions trying to catch carbon after we burn it, it would be fundamentally cheaper, safer, and just more effective to leave the fossil fuels in the ground and transition to renewables.
Section 5. The final verdict on CCS.
So, synthesizing all these competing facts into a mature, balanced final verdict, that is absolutely crucial for your essay conclusions. Ultimately, environmentalists, geographers, and policymakers generally agree on one main thing. CCS is not some magical silver bullet. We can't just build CCS plants and keep consuming fossil fuels exactly like we did in the 20th century. However, it shouldn't be totally discarded either. It's a potentially vital tool in our broader mitigation toolkit. To truly stabilize the carbon cycle and flatten that Keeling curve, CCS has to be deployed strictly alongside a massive increase in renewable energy, direct air capture technologies, and some really fundamental behavioral changes in how our society consumes energy. Now it's your turn to step up for your final exit ticket challenge. Based on the evidence we've covered today, can you clearly synthesize one specific way combustion alters global carbon flows and one robust, geographically sound reason why carbon capture and storage might ultimately fail to save us? Ask yourself this: is our reliance on futuristic technology just a convenient excuse to avoid changing our behavior today? Jot down your answers, keep thinking critically, and I'll see you in the next explainer.